We have a question here on electric field due to a continuous charge distribution. Given here is a long rod, 10 centimeter long, and it has a net charge of 50 microcoulomb distributed uniformly along its length. We are supposed to find the electric field generated by this charged rod at a position which is 10 centimeter away from both ends of the rod. Do you see that this is a straightforward application of what is taught in the theory session? Well, let me help you here. If this is the rod and this is the point P in question where we need to find the electric field because of this charged rod, consider x-axis and y-axis as shown. The net electric field at the position P will have two components, two perpendicular components, one along x-axis, Ex, and another along y-axis, Ey, let's say. And if this angle is taken as alpha and this as beta, then you know that for this kind of rod, which has a uniform charge distribution all along its length, the electric field at point P turns out to be such that Ex will be lambda by 4 pi epsilon naught r. What is r? The perpendicular length from the point in question to the rod I am speaking of, into sine of alpha plus sine of beta. What about y component? It will be Ey equals lambda by 4 pi epsilon naught r into cos beta minus cos alpha. What is lambda here? The linear charge density, that is the net charge on the rod divided by its total length. Do you see that in this case, the point in question is situated symmetrically with respect to the ends of the rod, in the sense it's equidistant from either ends of the rod. In that case, this is an equilateral triangle. This is 60 degree, this is 60 degree, this has to be 60 degree. Also, alpha will be 30 degree and beta will be 30 degree as well. In that case, cos beta minus cos alpha will give you 0. There is no y component of the electric field at the point in question in this case. What about Ex, the x component? Let's evaluate that. Ex will be lambda, which is total charge by total length of the rod. Total charge on the rod is 50 microcoulomb divided by the total length, which is 10 centimeter, into 1 by 4 pi epsilon naught will be numerically 9 into 10 to the power 9 unit divided by r. What is r? This r, if you look at this right angle triangle, turns out to be 10 centimeter sine 60 degree, right? In that case, it is 10 to 10 to the power minus 2 into sine 60 degree, which is giving you root 3 by 2. Let's simplify. This turns out to be 9 by root 3 or 3 root 3 into 10 to the power 7 Newton per coulomb. 3 root 3 is around 5.2. So the final answer is 5.2 into 10 to the power 7 Newton per coulomb. Now let's look at the options. The correct one is B. The next question we have here is on electric field generated due to a continuous charge distribution. Given here is the case of a straight line uniform charge distribution which extends on both the sides till infinity, and we are looking at choosing the right option among 4 given to us for the variation of electric field due to this kind of setup along the perpendicular drawn from the straight charge distribution, or the charge distribution along a straight line. All right. In order to do that, let's look at the electric field generated because of a finite straight line charge distribution. If this is the line along which charge is distributed in a uniform manner, Let's say these two are the ends, A and B, and we are looking at electric field at point P at a distance r, at a perpendicular distance r from this line charge. If lambda is considered to be the linear charge density, what do you mean by linear charge density? The total charge on this line divided by the total line length. In that case, if these two are the angles made by the ends of the rod or the line charge, alpha and beta, let's choose x-axis and y-axis as shown. The electric field generated because of this line charge at point P will have two perpendicular components, one along x-axis, another along y-axis. With the given situation, the x component of the electric field turns out to be Ex equals lambda divided by 4 pi epsilon naught r into sine alpha plus sine beta. What about y component? It turns out to be Ey equals lambda by 4 pi epsilon naught r into cos beta minus cos alpha. What we chose here is a finite length having line charge distribution. What if I consider the same line charge distribution to extend all the way till infinity on both the sides? Do you see that alpha and beta will become 90 degrees each? Exactly why I will write alpha and beta to be 90 degrees in this case. So your Ey actually turns out to be 0 then. What about Ex? Ex will be lambda divided by 4 pi epsilon naught r into sine 90 degree plus sine 90 degree, which is going to give you 2. This is the dependence of Ex on r. Let me write it as Ex equals 2k lambda by r. So what's the conclusion? There is no y component of the electric field, but the x component turns out to be 2k lambda by r. We are looking at the variation of Ex value with respect to r. This is something similar to plotting the variation of x versus y or y versus x for the equation x into y equals constant. What do you get that kind of graph to be? Rectangular hyperbola, right? Even in this case, Ex variation with respect to r turns out to be a rectangular hyperbola in nature on the graph sheet. Now, with these deductions in mind, let's look at the options. The right one turns out to be D. We have yet another question here on electric field due to a finite but continuous charge distribution. Given here is a finite length wire of linear charge density lambda coulomb per meter. Look at the options given. Among these, we need to choose the right one for the electric field magnitude at point P because of this line charge. Well, in order to do that, let's consider this finite length having uniform charge distribution. If you consider x-axis and y-axis as shown, then if the angle made by the two ends A and B at this point P with respect to the perpendicular D drawn here are, let's say, alpha and beta, in that case, the electric field at point P will have two perpendicular components. Let's call them Ex and Ey respectively. In terms of lambda, D, alpha and beta, Ex turns out to be lambda k divided by D into sine of alpha plus sine of beta. What about y component? It turns out to be Ey equals k lambda by D into cos beta minus cos alpha. This is straight from the discussion in the theory class. I hope you remember them. So we have got now the Ex and Ey component. In order to find the actual value of the electric field intensity at that particular position P, all we need to do is substitute the values of alpha and beta here and evaluate. These are the components. Let's find what is Ex and what is Ey. Ex turns out to be k lambda by d into sine alpha. Alpha is 30 degree, so sine 30 degree is half. Sine beta, beta is 60 degree, so sine 60 degree is root 3 by 2. Here is your Ex component. What about Ey? It is k lambda by d into cos beta, which is cos 60 degree, that gives you half, minus cos alpha. Alpha is 30 degree, cos 30 degree will give you root 3 by 2. Now that you have got Ex and Ey components, how do you find the E net? You have to add them vectorially, right? So the final magnitude of E net turns out to be square root of Ex square plus Ey square. Let's substitute and simplify. E net will be k lambda by d will be a constant from both the terms, square it and keep it as it is. Into, here you will have 1 plus root 3 whole square by 4 plus 1 minus root 3 whole square by 4. You can also draw that 4 in the denominator in common out. So it will be k lambda by d whole square into 1 by 4 and the square root into, now square it, expand it and then sum it up. You will have 1 plus 3 plus 2 root 3 plus 1 plus 3 minus 2 root 3 here. 2 root 3 and minus 2 root 3 will go away. What do you get? You get square root of k lambda by d whole square into 1 by 4 into 8. Simplify that and you get your final answer to be root 2 k lambda by d. That is your E net value. Now, let's look at the options. The correct one is A. Look at this very interesting question. We are considering here 3 uniformly charged lines, one along x-axis, another along y-axis, and the third one is along z-axis. Because of these lines of charges, with charge density being lambda, we are considering the net electric field at a point P whose coordinates are given to be A, A, A. What do you mean by that? In order to go there to point P from origin, you need to take x-axis, travel a distance along that by A, then take y-axis, travel by A, then take z-axis, travel by A. That's how you reach that position. Now, look at the options given here. It appears tricky, but let me tell you it isn't. If you consider one line at a time, the job will be easy. Let's say you have a line of charge here, an infinitely long one, with charge density being lambda. Here is a point P with a perpendicular distance, let's say d. What's the magnitude of electric field because of this infinitely long wire or line with uniform charge density lambda? In magnitude, it will be E equals lambda divided by 2 pi epsilon naught A. What about the direction? Well, if it is positively charged line, then at P, the direction of electric field will be away from that line. If it is negatively charged line, then it will be towards that line. Now, let's take one line at a time and consider the electric field because of that. We will choose our x-axis and y-axis as shown. Z-axis is, let's say, towards me, coming out of the plane here. And this is the wire I'm considering along z-axis. Here is the point in question. What's the perpendicular distance from this line to P? Well, this is A and this is A. Obviously, the perpendicular distance will be root 2A. In that case, if I call this E1 vector, the electric field because of this line alone, then in magnitude it will be lambda divided by 2 pi epsilon naught, perpendicular distance being root 2A. What about the direction? Since we are considering this line to be positively charged, we need to take the direction of the field to be away from this line. We need to choose a unit vector along it, right? This angle is known, it is 45 degrees. So, in this direction, a unit vector can be written as 1 cos 45 degree I cap plus 1 sin 45 degree j cap. What will that give us? Cos 45 degrees 1 by root 2, sin 45 degrees 1 by root 2. Root 2 will come common in the denominator. And that into root 2 will make it 2. There is another 2 sitting there. So, what will happen? Your E1 vector will turn out to be lambda divided by 4 pi epsilon naught A into I cap plus j cap. Do you see a pattern here? Now, let us consider the wire along y-axis this time. The field produced by that is, let's say, E2 vector. That will turn out to be lambda divided by 4 pi epsilon naught A into, I'm considering the line along y-axis. Remember, in that case, you will get here inside the bracket k cap plus I cap. And if you consider the line along x-axis next, the field because of that at this point will turn out to be lambda divided by 4 pi epsilon naught A into j cap plus k cap. All you need to do now is find the vector sum of vector E1, vector E2 and vector E3. What will that get us? E net, which is what we need. It will be vector E1 plus vector E2 plus vector E3. Simplify this and you will get lambda divided by 2 pi epsilon naught A into I cap plus j cap plus k cap. Right? So, this is your final answer. Look at the options. The correct one turns out to be B. We have here a question on the electric field generated by a uniformly charged ring. Look at this. We are given 4 options for the variation of this field along the axis of the ring, and we have to choose the right one. All right. I hope you do remember the expression for the electric field intensity in magnitude along the axis of the ring. It happens to be kq small r divided by capital R square plus small r square to the power 3 by 2. What is q here? The charge on the ring. What is small r here? The distance along the axis of the ring measured from the center of the ring. And capital R happens to be the ring's radius. If you draw, let's say, a ring like this with uniform charge distribution, and let's say the charge on it is plus q, and the radius of the ring is capital R. Do you see that R is equal to 0 here, and we are considering the extremities as well. R is equal to infinity on this side, R is equal to infinity on that side as well. We are looking at the variation of electric field intensity and magnitude all along the axis. How do you do that? Well, consider this expression. You know that at the center of the ring, the electric field intensity turns out to be 0 in magnitude. What happens to its magnitude on the either side? Let's consider one side at a time. If you take a position, let's say P in consideration, on one side, on the axis of the ring, you know that the electric field happens to be in this direction because of this charged ring, because it is positive in nature. What if the charge on the ring was negative in nature? In that case, the electric field would point in this direction, right? Exactly why there is a need to define an x-axis to account for the direction as well. Now, let's plot the variation of E with respect to R. At the center, R is equal to 0. Electric field intensity in magnitude is 0. Also, at R is equal to infinity, this electric field intensity becomes 0 as well. What happens in between? I hope you remember, the electric field becomes maximum in magnitude at small r equals R by root 2, capital R by root 2. So the graph will look like this. It increases and then drops off to become 0 only at infinity. Now, what happens on the other side? The same trend, right? It starts off at this position as 0, and on this side the electric field will be in this direction, opposite to that of x-axis, and it becomes maximum in magnitude at a position, let's say R is equal to minus capital R by root 2. It's here. And the magnitude decreases to become 0 at infinity on this side. But to account for the change in the direction on the graph, we will plot it something like this. It increases to become maximum at small r equals minus R by root 2, and then drops off to become 0 only at infinity. So this is how the graph going to look like. Now let's look at the options. Which one matches this trend? It's obviously option A.